Picture a crane sitting in open water, lifting a load that weighs more than the crane itself. Nothing solid beneath it. No bedrock, no foundation, no land. Just water, moving and shifting the way water always does. By every instinct you have, that platform should pitch forward and roll over the moment the cables take the strain. A heavy weight, lifted high, off to one side, on a surface that will not hold still. That is the textbook recipe for a capsize. And yet, it does not happen. The load comes up. The platform stays flat. The whole operation looks almost calm, almost boring. So, how does a floating object pick up something heavier than itself without tipping over? By the end of this, you will understand the four-part system that makes it possible, and why taking away any single piece would send the whole thing straight to the bottom. It starts with the part you can see but probably ignore, the platform itself. The pontoon. This is a massive flat-bottomed barge, and it is not big just to give the crew room to walk around. It is big because it has to displace an enormous amount of water. Remember Archimedes. A floating object pushes aside a volume of water equal to its own weight. That displaced water pushes back up. That upward push is what we call buoyancy. So the pontoon has to be large enough to displace enough water to support the crane, the counterweight, the crew, the machinery, the fuel, and eventually the thousands of tons of ship it is about to lift clear of the sea. Every one of those tons has to be answered by water pushed out of the way. But size alone won't keep it upright. A barge can be huge and still roll over. Notice the shape instead. The pontoon is extremely wide and very shallow, much wider than it is tall. That width is doing something specific. It's fighting the roll. Think of a canoe. Step a little too far to one side and it flips you into the water instantly. Now think of an aircraft carrier. You could walk from one edge of the flight deck to the other and barely feel the deck move. Same water, completely different behavior. The difference is the width of the hull. Engineers have a term for this: metacentric height. It's a measure of how hard a vessel resists rolling. The higher it is, the stiffer and steadier the vessel sits in the water. A wide, flat hull gives you a large metacentric height. It behaves less like a canoe and more like a dinner plate floating in a sink, almost stubbornly refusing to tilt no matter how you nudge it. That's why these crane barges are built with such an extreme width-to-depth ratio. The pontoon is doing two jobs at the exact same time. It provides the buoyancy to stay afloat, and it provides the width to resist tipping over. And all of that is true before anything has been lifted at all. That's just the platform sitting empty, because the moment the crane takes weight, a brand new problem appears. When the crane lifts a ship up on one side, all of that weight is suddenly hanging off one edge of the platform. Physics says the pontoon should tilt hard toward the load and just keep going until water pours over the rail. But it doesn't. The reason is sitting on the opposite side of the vessel, placed there long before the lift began. A counterweight. A massive, deliberate, enormous block of weight set down on the far side of the crane. Think of a seesaw. Put a child on one end and nothing on the other, and that end drops straight to the ground. Put an equal weight on the other end, and the whole thing settles into balance. The counterweight does exactly that. It sits opposite the lifting point and balances the load, keeping the platform from rolling toward the crane. And this counterweight is not small. On a large, sheer-leg crane, it can weigh as much as the ship being lifted. We are talking hundreds, sometimes thousands of tons of solid ballast, built into the structure of the vessel. It's positioned as far from the crane as the vessel allows, and that distance is not an accident. Distance multiplies its effect. The further out the weight sits, the more leverage it has, and the less of it you actually need to do the job. It's the same reason a long wrench loosens a stubborn bolt that your bare hand never could. Move the force further from the pivot, and that force gets stronger. And here's the key. That counterweight is in place from the very beginning. Before the cables go taut, before the load ever leaves the water. The balance is engineered into the vessel before the lift even starts. So the platform is wide, it floats, and it is balanced by a counterweight. At this point, it sounds like the problem is completely solved. It isn't. And here's the part that goes against common sense. You'd assume the most dangerous moment of the entire lift is when the ship is hanging high in the air, heavy and exposed and swinging. It isn't. The most dangerous moment is the instant the ship breaks the surface of the water. Here's why. While that ship is still partly submerged, the sea is secretly helping. The water is buoyant. It is holding up a share of the ship's weight, exactly the way it holds up everything else that floats. The crane is only carrying part of the load. The ocean is quietly carrying the rest, and the crew can feel that help in the cables. But as the ship rises and clears the surface, that help vanishes. Foot by foot, the buoyancy disappears, and the full, true weight of the ship transfers onto the crane. Think about that. The load the platform is carrying actually grows heavier during the lift, not lighter. The closer the ship gets to clearing the water, the harder the platform has to work. And right at that transition, the pontoon begins to tilt. Just slightly. A few degrees to one side. A few degrees does not sound like much. On a vessel doing a precision lift, holding a ship over delicate equipment, a few degrees is enough to ruin everything. That's where the fourth system comes in, and it's hidden completely out of sight, below the waterline. Underneath the deck, buried inside the hull of the pontoon, are ballast tanks. Multiple separate tanks, spread throughout the vessel, fore and aft, port and starboard. These tanks are filled with seawater, thousands of tons of it. The water inside them does not have to stay still. Powerful hydraulic pumps can move that water from one tank to another, and they do it while the lift is happening, in real time, second by second. If the platform starts leaning to port, water is pumped from the port tanks over to the starboard tanks, and the vessel levels back out. If the bow dips, water moves toward the stern. If the stern drops, water moves forward to lift it. This is what separates a sheer leg crane from a simple barge with a heavy block bolted to it. The counterweight is a fixed, static balance. The ballast system is active. It is alive. It thinks and responds. It is less like a statue standing rigid and more like a tightrope walker, constantly making tiny adjustments, shifting weight a little this way, a little that way, never perfectly still, always correcting before a small lean becomes a big one. So now the vessel can float, resist rolling, balance the load, and actively level itself against every shift. There is one piece left, and it is the part everyone actually looks at. The crane structure itself. Look at a sheer leg crane, and you'll see it isn't one tower. It's two huge frames, one toward the front of the vessel, one toward the back. Each one shaped like a giant letter A. These are the sheer legs. A-frames built from massive tubular steel members, thick enough that a person could walk through them, and the name of the whole vessel comes from them. They aren't twinned just for strength. They're twinned to spread the load. If every bit of the lifting force ran through a single point, that one spot on the hull would take a brutal, concentrated stress. The pontoon would have to be heavily reinforced right there, adding weight, adding cost, adding a weak point. By splitting the structure into two A-frames, the force travels down two separate paths into the hull. It spreads across a much wider section of the vessel, instead of stabbing into one place. It's the difference between carrying a heavy box pinched in one hand versus carrying it with both hands. Same box. The load is just shared and nothing gets overstrained. The deck area directly beneath those frames is the most critical structure on the whole vessel. It is reinforced with thicker steel and extra stiffening, because that is where all the force of the lift finally pours into the hull and gets absorbed. The cables run from the tops of both A-frames down to the ship being raised. As that ship rises, both frames carry the weight together, equally, side by side, like two people lifting in perfect time. So here's how it all comes together out on the water, in the real world. Before anything is lifted, the crew sets the ballast. Seawater is distributed through the tanks until the platform sits dead level. The counterweight is already in position. The shear legs are lined up directly over the lifting point. Every system is checked, and checked again. Then the hydraulic winches engage. The cables draw tight. The slack disappears. The steel begins to sing under tension, and the ship begins to rise. It is not fast. A lift like this can take hours. But speed was never the goal. Control is the goal. Every inch is deliberate. As the ship climbs, the buoyancy bleeds away and the weight grows. The pumps respond, moving water between tanks, holding the platform flat through every degree of change. And then the ship clears the water completely, thousands of tons hanging in open air, suspended from steel cable, and the platform beneath it sits calm and level, as if nothing remarkable is happening at all. That's the whole trick. A floating crane lifts something heavier than itself for one reason. 4 systems working at the exact same time. The wide hull resists the roll. The counterweight balances the load. The ballast actively corrects every shift. The twin frames spread the force into the steel. Pull out any one of them, and the lift fails. Leave them all working together, and a vessel can pick up an entire ship from a surface that never stops moving. But staying upright is only half the problem. A vessel doing a precision lift also has to stay in exactly one spot, holding its position against current and wind, sometimes without dropping a single anchor to the seabed. How a ship pins itself to one point of open ocean with nothing at all touching the bottom is its own strange piece of engineering. Subscribe, and that's the one we'll pull